Introduction. Ice hockey is a physically demanding sport that requires athletes to generate maximal levels of power and speed while maintaining balance while responding to on-ice movements of other players. This must be accomplished while participating in offensive and defensive strategies designed to maximize scoring opportunities for one's own team and minimize scoring opportunities for the opposing team. The merging of athletic skill and ability, proper physical conditioning, mental preparation, and appropriate nutrition intake with appropriate game strategies leads to successful performance on the ice during competition. Various physiological attributes contribute to successful sports and athletic performance with the combined interaction of the aerobic and anaerobic energy pathways, muscular strength and power, flexibility, and balance being important to the success of ice hockey in athletes. Consequently, the development of physiological profiles of these attributes helps in the selection of athletes who will perform at optimal levels during competition, assists in the identification of individual player strengths and weaknesses, and contributes to the development of successful sport-specific training programs. Skating ability is one of the most important factors that contributes to successful performance in ice hockey athletes. In an effort to better understand the role physical attributes have in on-ice skating performance, several studies have been conducted that examine the relationship between laboratory measures of performance and on-ice skating speed. Individual measures and combined batteries of tests include body composition, standing long jump, vertical jump, 3-hop jump, side shuffle, drop jumps, 1 repetition maximum leg press, running sprint test, and the wing gait anaerobic power and capacity test have been evaluated to determine their individual or collective contribution to on-ice skating performance. Collectively, the available research suggests that some, but not all, laboratory measures may have effectively predict on-ice skating performance in both men and women ice hockey players. In an effort to further examine the relationship between selected laboratory measures of physical performance and on-ice skating speed, we had athletes from the National Collegiate Athletic Association (NCAA) Division I intercollegiate ice hockey team assessed for body composition and then perform a Wingate anaerobic power test, an isokinetic leg dynamometer test, and an on-ice speed skating test. Specifically, the purpose of the study was to examine the relationships between the off-ice laboratory testing of body composition and leg strength and power and on-ice skating speed in these Division I men's hockey athletes. We also attempted to identify the best predictors of on-ice skating speed from the measured laboratory variables. The result of the study provided additional information on the use of laboratory testing to predict on-ice skating speed and assist in the development of effective training and conditioning programs. Methods. Experimental approach to the problem. All subjects were tested after 5 weeks of preseason strength and conditioning program that was directed and monitored by the Miami University Intercollegiate Strength and Conditioning staff. Testing occurred during the first week of October, immediately before regular scheduled ice hockey practice began for the 2008-09 season. This was a team of highly skilled athletes who participated in the NCAA Frozen Four Championship, finishing as national runners-up. All subjects were tested at the same time of the day to control the diurnal variations. Subjects were tested on 3 separate occasions with at least 48 hours between testing days. On the first day of testing, subjects reported to the Health and Human Performance Laboratory where they were measured for body mass and body composition. Immediately thereafter, subjects were tested for anaerobic power using the Wingate 30-second anaerobic power and capacity test. On the second day of testing, muscular force production was measured using an isokinetic dynamometer. On the third day of testing, subjects reported to the ice arena and performed an on-ice measure of skating speed using a sprint skating test. The same research technicians administered each individual test. The measurement of these dependent variables was then used to examine the relationship between off-ice laboratory testing of body composition and leg strength and power, and on-ice skating speed. Subjects: 21 males, 20.7 plus or minus 1.6 years, members of the men's university varsity ice hockey team who played the position of forward or defense participated in this study. All subjects read and voluntarily signed a written informed consent document and completed a health history questionnaire in accordance with guidelines set forth by the Human Subjects Institutional Review Board at Miami University. Subjects refrained from any prior exercise on the days of testing. Body mass composition. Height was determined using a stadiometer, and body mass BM was measured using a calibrated electronic scale. Body composition was assessed using air displacement plethysmography, BOD Life Measurement Incorporated, Concord, California, USA, according to the manufacturer's instructions. All subjects were tested 2 hours postprandial, avoided before testing, and were measured wearing only compressed shorts. Percent body fat, percent fat, and BM were used to calculate the amount of fat mass FM and fat-free mass FFM for each subject. Anaerobic power. Immediately after completing the assessment of body composition, the subjects were tested for anaerobic power using the Wingate 30-second anaerobic power and capacity test. All subjects performed a 5-minute warm-up and low-intensity cycling with the flywheel resistance equal to 1 kp and pedal speed equal to 60 rpm. At times, 1 through 4 subjects performs a submaximal 75 through 90% of maximum effort sprint of the 5-second duration. After completing the warm-up, subjects were given a 5-minute recovery period before performing the test. Anaerobic power and capacity were measured using a calibrated Monarch computerized cycle ergometer model 894E with the flywheel resistance set at 7.5 of individuals BM. Subjects began the test by increasing the pedaling velocity over a period of 5 seconds against an unloaded flywheel. When the cadence reached 120 RPM, the computerized cycle ergometer automatically dropped the weight-loaded pan, and the resistance of the flywheel was increased. Subjects were allowed to rise out of the cycle ergometer seat to a standing position during the test. Recent research has shown no difference in peak or mean power in the elite-level speed skaters during performance of a Wingate test when the standing or seated position. Power output was recorded in 1-second intervals during the entire 30-second test. The following variables were calculated from the collected data: peak power per kilogram body mass, peak power per kilogram FFM, average power per kilogram body mass, average power per kilogram FFM, average power for 0 through 5 seconds, average power through 5 through 10 seconds, and percent fatigue PF from the following formula: power drop divided by power peak times 100. Muscular strength. On the second day of testing, subjects reported to the laboratory for the measurement of muscular strength using a calibrated HUMAC isokinetic dynamometer, Stoughton, Massachusetts, USA. All subjects performed a 5-minute warm-up of low-intensity cycling with the flywheel resistance equal to 1 kp and pedal speed equal to 60 rpm. At minutes 1 through 4, subjects performed a submaximal 75 through 90% of maximal effort sprint of 5-second duration. After completing the warm-up, subjects were given a 5-minute recovery period before performing the test. Subjects were seated on the isokinetic dynamometer with the testing leg secured by Velcro straps and the upper body secured by a harness system. The fulcrum of the lever arm was adjusted to bisect the center of the knee joint. The bottom of the lever arm was secured at a position just superior of the ankle. Subjects were allowed 3 practice repetitions of increasing intensity, 25, 50, and 75% of maximal effort, followed by a 60-second recovery period. During testing, subjects performed 10 repetitions of concentric muscle actions at 120 degrees using a quadriceps and hamstrings, leg extension, and leg curl. Subjects were tested using both their right and left legs with the order of the legs randomly assigned. The following variables were calculated in Newton meters for both muscle groups: quadriceps and hamstrings for both legs, left and right, peak torque per kilogram, FFM, and total work. On ice skating speed. On the third day of testing, subjects reported to the ice arena. Subjects were tested while wearing full ice hockey equipment, but without their ice hockey sticks. The repeat skate sprint test RSS requires subjects to perform 6 maximal effort sprints with a 30-second recovery between trials. Figure 1 illustrates the RSS and point at which the skating time was recorded. Subjects were given a 5-minute perform the individualized warm-up and then a rest period before testing. To start each trial, the subject stood with both skates behind the goal line and on command sprint skated to the goal line of the other end of the rink. Once both skates had crossed the goal line, the subject immediately stopped, turned, and sprinted. The time required to go from the start goal line to the opposite goal line, a distance of 54 meters, was recorded as the first length skate, FLS. The time required to skate from the starting goal line to the opposite goal line and then back to the near blue line, a distance of 89 meters, was recorded as total length skate, TLS. At all times were recorded manually, losing a digital stopwatch by the same 2 research assistants. The average of the 2 times for each sprint was used in the data analysis. After completion of the tests, the following variables were determined: fastest, FLS, FLS fastest, fastest TLS, TLS fastest, average of the 6 FLS, FLS average, and average of the 6 TLS, TLS average. Average linear movement, LM, was calculated for the FLS skate, FLS fastest LM, TLS fastest, TLS fastest LM, FLS average LM, and TLS average LM using the following formula: LM times kilograms per meter per second equals BM kilograms times skating velocity meters per second. The fatigue index, FI, for the FLS, FI, and the TLS FI was calculated as follows: fastest skate time minus slowest skate time divided by fastest skate time times 100. Statistical analysis. Mean and SDs were calculated for all variables. To quantify the strength and direction of many bivariate relationships, Pearson correlation coefficients were calculated. Statistical correlations was observed with p less than or equal to 0.05. The establish of the ability of the laboratory measures to predict on-ice skating speed, multiple regression analyses were conducted using stepwise forward selection. Separate regression analyses were run for each of the on-ice criterion variables. Our goal was to identify a limited number of laboratory variables that account for the greatest variance, i.e. r squared, in on-ice skating speed, and therefore optimize the prediction of on-ice skating speed. At each step in the following selection, a p-value of less than or equal to 0.05 was the statistical significance criterion to enter variables. All analyses were conducted using SPSS version 16.0. Results. The mean and SDs for the physical characteristics, anaerobic power, isokinetic force production, and on-ice skating speed are reported in tables 1 through 4. The subjects were physically fit with high levels of anaerobic power and capacity, high isokinetic force production, and fast skating speeds. We classified the various tests into 4 categories: on-ice variables, anthropometric variables, isokinetic variables, and wind gate variables. A matrix of intercorrelations which presents the correlation coefficient in pairs of variables is shown in Table 5. Not surprisingly, the on-ice skating performance variables were strongly related to each other within the category. For instance, FLS fastest time and TLS fastest time were strongly correlated. R equals 0.85, P is equal to 0.001, indicating that FLS fastest times could account for approximately 73% of the variance in TLS fastest times and vice versa. Likewise, FLS average times and TLS average times were also strongly correlated. R is 0.89 and P is less than 0.001. Measures of linear momentum had several fair correlations. P 0.25 with skating times and skating fatigue indices. Finally, skating times were in several cases moderately correlated, P 0.5 through 0.75, with skating fatigue indices. An example was that TLS fastest was significantly correlated with TLS FI. On ice skating times, FLS average and TLS average were moderately correlated to percent body fat, and such that a greater percent of body fat was related to a slower skating speed, figure 2. On-ice skating times were also significantly correlated with wing gait, anaerobic power, and capacity measures. Specifically, FLS fastest was correlated to PF, figure 3, and FLS average was correlated to wing gait peak power per kilogram. These correlations indicated that subjects with a quickest FLS fastest time had the greatest percent fatigue during the wing gait test. And the subjects with the best FLS average skating times were those subjects that produced the greatest peak power per kilogram body mass during the wing gait test. On-ice skating times were not significantly correlated to any isokinetic dynamometer variables. Skating fatigue indices were not significantly correlated to any predictor variable. Measures of linear momentum were significantly correlated to many of the predictor variables, including those from the isokinetic dynamometer and the wing gait tests. This was expected because of body mass influencing several of the isokinetic force production and anaerobic power capacity variables. The multiple regression analysis predicting FLS fastest yield and PF in the wing gait test as the only significant predictor variable. The multiple correlation coefficient was 0.48 with an adjusted R squared of 0.19, indicating that conservatively 90% of the variance in skating speed for the FLS was predicted by percent fatigue on the wing gait test. For the regression analysis of the criterion variable, FLS average percent fat was the only significant predictor variable. The multiple correlation coefficient was 0.53 with an adjusted R squared of 0.24, indicating that conservatively 25% of the variance in FLS average was predicted by percent fat. Similarly, the multiple regression analysis predicted TLS average yielded percent body fat as the only significant predictor variable. Multiple correlation coefficient was 0.57 with adjusted R squared of 0.29, indicating 29% of the variance in the TLS average was predicted by the subject's percent body fat. Several multiple regression analyses using TLS fastest and both skating fatigue indices, FLS FI and TLS FI, as criterion variables yielded no statistical significance predictor variables. Discussion. The subjects in the current study were experienced elite-level ice hockey players. The physical characteristics of body mass and percent fat compared favorably to other university-level ice hockey athletes and National Hockey League entry draft ice hockey players. The anaerobic power and capacity measures were reported in the current study fall into the elite category for male intercollegiate athletes and are higher than previously reported for male ice hockey players. The differences between our wing gait anaerobic power and capacity data and that reported previously could be partly because of allowing subjects in the current study to rise out of the seat to a standing position during performance of the wing gait test. Although recent work with elite speed skaters showed no difference in anaerobic power between seated and standing position, we were unable to locate any leg isokinetic force production data from previous research ice hockey players to compare to the current study. The data from the current study are similar to isokinetic force production in young French and Swedish professional soccer players. Similarly, it was difficult to make comparisons of on-ice skating speed and previous studies because of different distances used to measure skating speed. The differences covered by university and junior A hockey players in the study by Watson and Sargent were similar to the FLS 54.9 meters and TLS 90.4 meters, to the current FLS study 54 meters and TLS 89 meters. We reported faster skating times for both the FLS and TLS. It was important to note that fatigue index from the current study for both the FLS and TLS is similar to that reported by Watson and Sargent. In conclusion, the subjects in the current study had very high levels of anaerobic power and isokinetic force production and fast on-skating speeds. Successful performance in ice hockey requires athletes to develop well-rounded fitness, including high levels of anaerobic power, aerobic endurance, muscular strength power, and endurance. on-ice skating speed is only one of the many important factors contributing to successful performance, and improving skating speed should be a focus of training and conditioning programs and a criterion measured for selection of athletes to competitive teams. The major findings of the current study suggest that the following laboratory measures can be best used to evaluate and predict on-ice skating speed and skating power in men's intercollegiate ice hockey players: percent body fat, isokinetic force production in the legs, and anaerobic power. Our results from the isokinetic testing and the Wingate anaerobic power test support that those previous studies in that their ability to produce force and power is very important for successful performance in men's ice hockey. For example, Burr et al. Has demonstrated that leg power, as measured by a vertical jump test, was moderately correlated with National Hockey League entry draft selection order. Also, Watson and Sargent found significant correlations, 46%, between a 40-second Wingate anaerobic capacity test and the RSS test in university and junior A-level hockey players. Fralinger et al. Has demonstrated that a 35-meter on-ice skating speed could be predicted by a 30-meter sprint and 3-hop jump test. Wingate mean and peak power and vertical jump height. The correlation matrix presented in Table 5 illustrates the statistically significant relationships between anaerobic power and force production in the legs and several measures of skating speed. It is interesting to note that the moderately strong relationship between percent body fat and measures in on-ice skating speed, figures 2, 3, and Table 5, is our belief that because the subjects in the current study are a homogeneous group of elite ice hockey players, that any factor that would reduce skating speed would be an important contributor to skating ability. Excess body fat would be represented by a higher percent body fat and would effectively reduce skating speed by contributing to the mass that must be moved on the ice but is not contributing to force production. Other investigators have also demonstrated the ability of body mass index score, which included a measure of lean body mass and body composition, to predict draft entry and transition into the National Ice Hockey League. The findings of the current study and those previously published should be useful for athletes, ice hockey coaches, and strength and conditioning personnel wishing to develop effective training and conditioning programs for ice hockey players. As part of the complete training program, ice hockey athletes should regularly engage in activities that promote increased force and lower production in the legs. The use of prolonged endurance activities that hinder development of force and power production should be minimized, because these types of activities have been shown to hinder development of force and power production in muscle. There may be several limitations of the study worth discussing. First, the measures of on-ice skating times were made using handheld stopwatches as opposed to electronic timing devices. The effect of this potential limitation is minimized by having multiple timers who are experienced at measuring skating times. A second limitation would be the level of motivation of the subjects for performing the Wingate anaerobic power and capacity test and the repeat skate sprint test. Both of these tests are physically demanding and considerably fatiguing. We believe, however, that this group of intercollegiate athletes was highly motivated for each test and therefore performed to their maximum capabilities. Finally, there may be a concern about the lack of familiarity with performing the isokinetic dynamometer test. We attempted to minimize this during testing by having each subject perform 3 practice trials with each leg before data collection occurred. We also believe that the high level of motivation in the subjects to perform well helped minimize any limitation brought about by unfamiliarity in the test. Practical applications. The results of this investigation indicate that coaches and strength and conditioning professionals can use laboratory testing of select variables to assist with assessing and increasing the on-ice skating speed of elite-level ice hockey players. This information can be valuable for monitoring and predicting skating performance when ice hockey athletes do not have access to skating facility, Information from the laboratory measures can be used to develop effective strength and conditioning programs that will alter body composition and leg strength and power in a manner that will improve on-ice skating speed. Specifically, strength and conditioning programs that promote lower percentage of body fat and high peak power will be best facilitate improvements in on-ice skating speed. The improvement in on-ice skating speed should contribute to overall development and improvement of performance in highly trained male ice hockey athletes.